So review for the final. Like I said, we're going to be jumping around a lot. So what I'm going to do is I'm going to highlight some of the instructions, especially if you take a look at number 1 here, which says factor. Instead of writing the steps or writing the clues for factoring every single time we see it, I'm going to use this space here to the right to list pretty much everything we've kind of covered regarding factoring. So anytime we have a problem later on that says factor, we can make a little note in the margin that says refer back to page 1. That way we can kind of navigate our way more efficiently. So off to the right here, this little subtopic is going to be all things factoring. First thing, you must always check for a greatest common factor first. Always check for greatest common factor first. There will not always be one, but you must always look for one before you do any other kind of factoring. Then after that, after the greatest common factor is either dealt with or at least, the very least considered, then what you do next depends upon how many terms you have. And I'll explain. So the first, I'm going to start from the smaller case and work my way up. If you have 2 terms, which as we know is a binomial, this is going to be the situation where we consider the difference of perfect squares. Now, we had a little mini formula there for that. If it helps you, great. I'm going to jot it down. If it didn't, there's at least one in here where we do the difference of perfect squares. So we will get some practice in later. But the formula was that if you had something squared minus something else squared, that automatically factored into the first thing being squared plus the second thing being squared. And then a second binomial where you had the first thing that was being squared minus the second thing that was being squared. So again, that's for if it's 2 terms. If it's a binomial and you're still trying to factor, consider the difference of perfect squares. If it's 3 terms, or in other words, a trinomial, this is where we considered the asterisk method. Now, the asterisk method did require it to be in a particular format, which was ax squared plus bx plus c. So descending order, it had to be quadratic, meaning the highest exponent was 2. If that was the case, you then could pull the a, b, and c for the actual asterisk itself. So that was a times c on top, a on either side, b on the bottom, and of course the 2 missing, that's where we had to kind of navigate and find the 2 values that multiply to equal the top, but added to equal the bottom. And then the final case that we got to, and we didn't practice it as much because it's a little less common, and that was if we had 4 terms. And for 4 terms, that's where we considered factoring by grouping. Now that's where we split it in half and find the little greatest common factors and work our way through it. And I'm pretty sure we have one example in this packet for that as well. So at any point throughout this review, we come across something now that says to factor, I'm going to say, let's refer back to page 1. This is where all that information is kind of packed in there nice and neat. So right off the bat, we do have a problem here that says to factor. So what's the first thing we look for first? Greatest common factor. So taking a look at the example here, does there appear to be a greatest common factor?
No.
No. So if it helps, if you need to see those hidden coefficients, you're always more than welcome to write the ones in there. But because of the ones only have a factor of 1, so that doesn't change much. And because they don't all have at least one of the same variable, I would agree there's not really a useful greatest common factor here. So then I look at how many terms I have. In this case, it's a trinomial, so 3 terms, which makes me consider using what? The asterisk method. And for that, I need to know my A, which is 1, my B,
1,
which is 1, and my C is a negative 12. Okay, so then I draw my little asterisk here, just an X with a horizontal line through the middle. I'm going to have A times C on top, so 1 times negative 12 will give me a negative 12. A on either side, those will be my 1s. B on the bottom is also a 1. Now you will have access to the factor pair list for the final. So this is where I would check the list of factor pairs for 12. I'm looking for 2 numbers that would multiply to equal negative 12, but also add to equal positive 1.
Three and 4.
3 and 4.
Negative 3.
Well, let's do a quick check. Worst case scenario, we're wrong and we adjust. So if we do a quick mental check, negative 3 times positive 4 will give me a negative 12. Negative 3 plus positive 4 will give me that positive 1. So those do check out. And from that, we get these 2 special pairs. Do either of them simplify at all?
No.
No. So from those 2 special pairs, since they're not simplifying, we bring back whatever letter we were using for the variable, which in this case was an n, and it's going to give me the 2 binomials that I need for this to be completely factored. So it looks like I get 1n minus 3 and 1n plus 4. I don't see one exactly like it.
B.
It would be B. So it's okay that they're in different order? Absolutely. So B would be my correct answer here. So which binomial comes first is not important. What is important is that you have those 2 exact binomials. Good. Number two uses a skill that we've had, but it phrases it a little bit more differently than what we're most accustomed to. But what I'm actually going to pick out first from the request here, it does say identify the zeros from the quadratic equation. And I'm going to hold on to that statement there, or those 2 words, quadratic equation. We spent 2 days solving quadratic equations. One was by factoring One was with the quadratic formula. And we'll talk about the quadratic formula later. But for this one, I'm going to make a little note section. Solving quadratic equations by factoring. And again, a lot of what I'm putting here are abbreviations of what we've done in the past. If you need more detail, more depth, feel free to find those corresponding lessons. The notes should have that extra information that you need. This is just meant to be just a nice, think of it as one giant sticky note of all the things we would like to try to remember. So for solving quadratic equations by factoring, first thing we needed to do was make sure we set the equation equal to 0. And for that, I'll make a little side note. Sometimes we'd have to move terms as needed. So if we had something on, if we had terms on both sides, that's where we added or subtracted things to get everything kind of slid to one side of the equation, setting the other side equal to 0. Second thing we do is factor. Now, I'm not going to dwell on that word factor too much because we just wrote down a little section of notes up above, all things about factoring. So I'm not going to go into detail there because we already did that. Step 3 is to set each factor equal to 0 separately. And that was thanks to our old friend, the zero product property that said, if you have a bunch of things multiplied together, therefore factors, and it's set equal to 0, at least one of those factors, one of those pieces must themselves be 0. And then the fourth and final step, and this one's kind of informal, solve each, I'm going to call it them little equations individually. So I'll leave that there for just a moment as you're jotting it down. So again, anytime and anywhere through the rest of this packet, if there is something that's having us solve a quadratic equation specifically by factoring, I'm going to say, again, refer back to page 1. We're not going to write this every time we need it. We've written it once, we know where to find it. Now, as I mentioned here, this one is worded a little bit differently. In particular, unlike the quadratic equations that we've had so far, this one has 2 variables, but there's actually a clue word here that you'll end up going into more depth with Andrea in Algebra 2, and that is that it's specifically asking us to identify the zeros. So this one is asking us to identify the zeros. Now, when you get to Algebra 2 with Andrea, she's going to have a section about solving these equations. You can actually solve them probably a variety of times. And what you're going to learn is that there are some terms that are actually interchangeable. And those terms are, regarding quadratic equations, solutions, roots, zeros, and x-intercepts. So solutions, roots, zeros, x-intercepts are all interchangeable terms because they all describe the same thing. The only difference is that in some scenarios, one term is a better descriptor than the other. For example, x-intercepts would make more sense if you were graphing, whereas solutions would make more sense in terms of solving an equation. But here they use the phrase zeros. And what that actually allows me to do is to say, okay, I'm really just asking myself, what would happen if y was 0? So if you were to reimagine this equation as saying 0 equals x plus 11 times x minus 5. This looks more like the equations we've solved, last week. In fact, if I refer back to the list that I jotted down earlier, it looks like the equation's already set equal to 0. And lucky for us, it also appears that it's already been factored. So that allows us to jump directly into step 3, which is to set each of those binomial factors equal to 0 separately. So thanks to the zero product property, we know that either x plus 11 has to equal 0 or x minus 5 has to equal 0. And what we do from there is we just solve each resulting equation one at a time. How would you solve the first?
Minus 11.
Minus 11 from both sides. So I get x equals 0, take away 11 is negative 11. What about the second one?
Add the 5.
Add the 5 to both sides. So I guess that x by itself, 0 plus 5 gives me 5. So my two zeros or solutions or roots, again, you're going to learn a lot of different terms to describe the same thing. In this case, my zeros here are negative 11 and positive 5. So moving on to number 3. Number 3 is a bit busy here because I'm going to actually also squeeze in a little bit of additional notes as well. I'm going to have to try to squeeze mine in here in the middle because it's asking us to find and describe the error in the problem below and then solve it correctly, showing all work. Now, it doesn't specifically identify what type of equation this is, but as I'm looking at it, it doesn't appear to be quadratic. So the steps we wrote down up above don't necessarily apply here. So even though it doesn't say it specifically, this is what we refer to as a single variable linear equation. And I'm just going to kind of abbreviate that to say solving linear equations. So notice I'm leaving the room there on the right because we are going to have to solve this one correctly. But I'm going to squeeze in the steps here. Again, this goes all the way back to unit 1. So it's been a minute. But just as a refresher here, first thing we always check for or should catch our eyes. Greatest common factor is quadratic equations. We're going all the way back to linear. So should be on there. So solving linear equations, first thing we should always, or that should always catch our eye, should be those parentheses. And anytime we see parentheses, hopefully we think about distribution. So this is going way back. After you've taken care of the parentheses, second thing we always check for was like terms. Toby, that was your moment. Those like terms, if we see any, all we have to do there is combine. If you recall back, we didn't have to do any fancy switches, no opposite signs. And part of that reason, as a little reminder, is that those like terms, in order to be considered like terms, must be on the same side of the equation, that is. Because otherwise they weren't like terms and therefore couldn't be combined. Third thing you consider is if the variable is on both sides. At this point, technically, I said you could move either, but my recommendation was usually to move the smallest. Now, Leanna, I know you typically went a slightly different route. You always like to move yours to the left, which meant that sometimes you were moving the smallest, sometimes you were moving the largest. But as we can probably attest, that still worked. Just meant you had a negative later on that sorted itself out. No big deal there. That's just a recommendation. And then the fourth and final thing we had to do was to get the variable by itself. Kind of running into my workspace here. So anytime we have to solve linear equations now throughout the rest of this packet, we will again refer back to page 1. Seems like page 1 has a boatload of information that we can refer back to. Now, again, that was just kind of the side note section. We still have to actually figure out what this person did wrong while also simultaneously solving it correctly ourselves. And I would actually focus there first, because if we follow our process, checking their steps as we go, eventually we're going to find a moment where we went 2 different routes. So what should catch your eye first in this problem here? Parentheses. So on the right here, we have parentheses, and it looks like we should be distributing a -8. So that'll actually be my first step. So I have 3n minus 5. Make sure I give myself enough room here. Equals -48 from the -8 times 6 minus 40n. Put my good old guideline in there, keep us on track, hopefully. How does that compare to their first step? They did it? So step 1 looks good. Okay, so then I come back to mine. Again, try not to recreate their mistake by looking at their work too long. So after parentheses, what do we check for next? Mm-hmm. Are there any like terms?
No.
I don't see any. At least what appear to be like terms aren't on the same side of our equation. So step 2 really doesn't apply here. Next thing I consider then is whether or not the variable is on both sides, which in this case it is. If we're going with my recommendation, which one would you suggest moving? The smallest, which would technically be the -40n, because all negative numbers are smaller than positive numbers. How would you make that -40n disappear from the right? Turn it to a positive or add it. Yep. So we'll use a positive 40n, but we have to make sure we use one on the other side as well. And there is a term there that's similar to it that we can actually add it to. So that takes it away from the right-hand side. 3n plus 40n gives me 43n. The -5 drops down. So does the equal sign. So does the -48. So I have 43n minus 5 equals -48. Let's take a look at their step. Their second step is wrong. Why? What happened?
And they just moved the 40 in, they didn't.
So we're,
It didn't
we're-
add
they didn't add it. It looks like they subtracted it, or as Leanna was saying, it looks like they just plucked it off the right-hand side, dropped it on the left-hand side. And we know you can't just change which side of the equation it is on without actually making a change to the value itself. So in particular, the problem in step 2 is that -40n. We added it to both sides. Looks like they subtracted it from the left. Side note, Marissa, I just saw your chat. Yes, this is the final review. And before we break today, I can catch you up on anything that you need to catch up on. All right, so while we found the error, before I forget it, let's go ahead and describe it before we finish solving this the rest of the way. So in step 2, we'll say that they subtracted 40n from the left instead of adding 40n to both sides. Now, remember, once you find the mistake, is there any point following their steps the rest of the way through?
Yeah, I want to know the real answer.
Well, yeah, we're going to follow our steps the rest of the way through, but
Not theirs.
their steps the rest of the way are going to be wrong because now they have incorrect values. Because if you look, subtracting their 40n from the 3n, they got a -37n. We have a positive 43n. So every step from here on is obviously going to be wrong to some degree. So I'm done looking at their work. Let's see the rest of our work through. So we took care of the parentheses. There were no like terms. We got the variable to one side. All that's left is to get that variable alone. What would you move next? The -5, and how would you move it? Add 5 to both sides. So that leaves me with 43n on the left. Bring down the equal sign. -48 plus 5 gives me a -43. What's left to move?
You divide by the positive 43.
Divide both sides by that positive 43. So I end up with n by itself equaling -1. Which if I, again, didn't dwell on it too much, but they got a crazy answer of 43/37. We found out that the answer is actually a -1. And that's why I tell you, technically, if you wanted to boil it down and oversimplify their mistake, they got a sign wrong. One sign was enough to throw off several steps, which is why I always suggest take your time, slow down, write neatly so you can follow your own process if you need to go back and double check. So yeah, so it's kind of crowded there with that extra set of notes there dropped in the middle. But now we even got to see it in action and we corrected someone else's mistake. So yeah, like I said, page 1 here is going to be chock full of information, and those who came in a little bit later, you'll be able to go back. This will be available for you guys to come back and jot down as well. So don't worry about scrambling just yet. All right, number 4, we're almost done with our first page. It's only been, 45 minutes. Number 4 is asking us to write the slope-intercept form of the equation of the line that goes through the point 5, 8 and has a slope of m equals 3. So a couple things we're going to pick out real quick. First off, slope-intercept form is y equals m times x plus b. And as a quick recall, m is always our slope. B is always our y-intercept. Well, good news. It gave us the slope, m equals 3. So we're technically already halfway there. Unfortunately, if I zoom out again, unfortunately, instead of giving me the y-intercept, it gave me a point. So I have the slope, but I only have a point, and it's not the special point that is the y-intercept. Well, if I zoom in here real quick, I know that a lot of the times when we had points in the past, we thought of it as being an x coordinate and a y coordinate. So the 5, I'm going to label it as my x1, and the 8, I'm going to label that as my y1. Now let's think about what information we have here. We're working towards slope-intercept form, but I don't have the slope and y-intercept. What I do have is a point and the slope. Do you guys recall anything that allowed us to use those bits of information together?
I took the y1 minus the yx1.
You're kind of, okay, so you're kind of remembering it. Its name was actually, it hit it right on the head. It was called point slope form. But Lana, you're in the process of trying to read it out to me. We have enough information right now to use point slope form. And as its name suggests, all you need for point slope form is a point, which we have, and the slope, which we have. But in case you have forgotten, point slope form is y minus y1 equals m times x minus x1. And because I usually do things very intentionally, you'll notice all the pieces that I need for point slope form have already been labeled. Now it's just a matter of dropping them into the appropriate locations. So we'll have y minus y1, which is my 8, equals m, my slope, which we were told is 3. And then in parentheses, we'll have x minus x1, which I've labeled on my 5. Now, the good news is we have the equation for this line, but what form did it need to be in? Slope-intercept form. Well, right off the bat, there's something that catches my eye that's never in slope-intercept form, parentheses. And when I see parentheses, I have the urge to do what? Distribute. Let's see what happens when we do that. So let's distribute the 3 into the parentheses. I'm going to get y minus 8 equals 3 times x, which is just 3x, 3 times negative 5, which is a negative 15. Okay, a little bit better. But what else is usually true about slope-intercept form? Sometimes there's, well, in slope-intercept form, there's not usually like terms, because if there were, we would have combined them. But if you're looking at slope-intercept form, we usually have y equals mx plus b. Here I have y minus 8 equals 3x minus 15. Anything different jumping out right now? There's a negative 8 with the y, whereas y is usually by itself. How would you get that negative 8 out of there? So add that 8 to both sides. That gets rid of it here on the left, leaving the y by itself, which I like to see. And then on the right, 3x just falls on down. We didn't mess with it anymore. Negative 15 plus 8, negative 7. That's it. We found it. Our equation in slope-intercept form is y equals 3x minus 7. Not too shabby. So already we've grabbed things from unit 4, unit 2, and unit 1. First page, we've spanned most of this course very quickly. All right, next page, number 5. This one hopefully is very fresh in our minds because this is a radical. And yesterday we simplified radicals. So as a little reminder here, when you are simplifying radicals, to kind of oversimplify what we did yesterday, what we did was find hidden perfect squares. Find hidden perfect squares because we like perfect squares inside square roots because you can take the square root of them very cleanly. But as we kind of encountered yesterday, you don't always get perfect squares in there. So you kind of got to try to break down what you've got, looking for any perfect squares that may be hiding. So for this one here, I'm going to jot it down again. We have 2 times the square root of 45a b to the 3rd. So the 2 is already outside. Not much I can do with it right now, but everything else inside, as it's currently written, does not appear to be a perfect square. So we're going to break it down, starting with the coefficient 45. Can you think of any factors of 45 that themselves are perfect squares? 5 times 5?
9 times 5.
9 times 5. Which of those two numbers are you most interested in?
9.
The 9. 9 is a perfect square. So we'll come back to that here in just a moment. What about the A?
Bring it down.
Can't do anything with it?
No.
What do we, when it comes to variables, how do we know we have perfect squares?
If it's squared.
If it's actually squared.
Yeah.
So I really like my variables to be squared in order to be considered a perfect square. Well, there's just not enough A's there to be considered a perfect square. But then I get b to the 3rd, and now there's too many b's.
Minus and 12. Take a b out.
Break a b off. Okay. So b to the 3rd is the same as saying b to the 2nd times b, kind of reverse engineering our exponent properties, where we know that when you multiply the same base, you add their exponents. Well, we just did that in reverse. We broke one off. There's still 3 b's under there. There's still 1a under there. 9 times 5 is still 45, but now we've got it to where we can actually spot some perfect squares. And I like those perfect squares because those are the pieces we can remove. So can I take the square root of 9?
Yes.
What is the square root of 9? 3. So taking the square root of 9 takes the 9 out of the radical. Can I take the square root of 5?
No.
No. Can I break 5 down any further? Nope. It's a prime number, so it's trapped inside. What about A?
No.
There wasn't enough there to group it into 2. There was only 1, so it's not a perfect square, so it's trapped inside as well. Can I take the square root of b squared?
Yes.
What is the square root of b squared?
B.
Just a b. So it is gone from inside my radical. Can I take the square root of b?
No.
No, for the same reason I couldn't take the square root of a. There's just not enough there to be a perfect square. So what we just removed is going to be multiplied together, but because there's something already outside, it's going to have to multiply with that as well. So what is now outside my radical? 6b. And although we tried really hard, what's still left over inside my radical?
5AB.
5ab. Look at the options. That is b. Good. So that was as recent as yesterday. Number 6. Sketch the graph of the function y equals x squared plus 4x plus 3. Identify the axis of symmetry, identify the vertex, identify the y-intercept. Well, guess what? We didn't do that. We ran out of time. We didn't get to do that, but you're in luck. That was one of those bonus lessons that you'll still get to do in Algebra 2. You'll spend a day graphing quadratic equations. So this will come up again. And you have, technically, you already have most of the skills to do it. I'm not going to test you on it because we haven't had the practice for it. So number 6 will show up on the final, but that it will be crossed out. You do not have to attempt number 6. Number 7. Number 7 is asking us to both solve and graph the compound inequality. And this compound inequality, you can tell there's 2 of them in there because of the 2 separate inequality signs. Now, this one I'm not going to go into too much notes on because the one on the final will look very similar to this one. But just as kind of a side conversation here, we had 2 types of compound inequalities. We had the and inequalities, which when graphed typically were 2 points and we shaded between. But we also had or inequalities, in which case we had 2 points and we shaded opposite directions. Again, if you want to go back and look at that in more detail, that's going to be Unit 1. I think it was like the last lesson of Unit 1. Unfortunately, there's not a video for that one, but the notes are up there. Now, another thing that we hopefully recall is that in order to determine which type we have, the trick I like to use is if you see the word or, it's an or inequality. Everything else is an and inequality. So guess what this one is? An and inequality. Now, this one's going to take a little bit of space. So since we're not using the space up above here, what I'm going to do real quick is copy this one down. And so I don't have to try to cram my work into one space here. So I'll have 4b plus 18 is less than or equal to negative 12b minus 14 is less than or equal to 14 minus 5b. Now, this is traditionally how most and inequalities will be presented anytime you're solving them. And if you try to solve them while they're written like this, it's not worth the headache. Some people think, oh, I'll try to do a shortcut. I'll be able to keep track of things. Don't overstretch yourself. What we did when we were solving and inequalities that looked like this is we reminded ourselves that everything that was in between those 2 separate inequality signs was all the information that we had to make sure that we shared between the 2 inequalities. And because I know that, then I should then be able to write them as two separate inequalities that I can then go through and solve. So the two inequalities I will have are going to be 4b plus 18 is less than or equal to negative 12b minus 14, and negative 12b minus 14 is less than or equal to 14 minus 5b. Once they're separated, it's just a matter of solving them, very similar to the same way we would have solved if these were equations. I'll put my little guidelines in here. Guess how much space I have or how much space I'll need. And then we're going to work through these one at a time to solve. So I'm going to start on the left one. Running through the same steps as if we're solving a linear equation. Do we have any parentheses?
No.
No parentheses. Any like terms?
Yes,
Where's the like terms?
but not on the same side.
So are they like terms?
Oh, no.
No. So like terms technically would not apply here. So the third thing I check for is the variable on both sides?
Yes.
Here's giving me a head nod. So typically I would suggest moving the smaller of the two, which in this case would be the negative 12b. So I do the opposite, which is a positive 12b on both sides. It gets rid of it on the right. I get 4b plus 12b, which is 16b. Bring down the positive 18. Bring down the less than or equal to symbol. Bring down the negative 14. Then the only thing that's left is to get the variable by itself, which is on the left side. So what are we going to start pulling away from that side? The 18. So we'll do the opposite. We'll subtract 18 from both sides. That removes it from the left, leaving me with 16b is less than or equal to negative 14. Take away 18, I believe, is negative 32.
Yeah.
And then what's left to do? Divide both sides by the 16. So I end up with b is less than or equal to negative 2. Now I got a negative. I seem to recall that's usually where I flip my sign, right?
But you're not dividing by the negative.
Good catch. I didn't divide by a negative. It's not whether or not you see a negative, it's whether or not you divide both sides by a negative value. And here I divided by a positive 16. So no bubbles, no troubles. So I've got half of the problem solved. Now I need to jump over and solve the second half so we can then work on piecing them back together. So on the right, just to kind of pick things up a little bit, no parentheses, no like terms, but the variable is on both sides. Now, technically, the negative 12b would be the smaller of the two. Would you like to move that one, or would you like to see what happens if we move the negative 5b? You want to see what happens when we move the negative 5b? It's a good practice exercise because it's going to work out either way. So let's say I accidentally thought negative 5b was the smallest, so I would add 5b to both sides. So that removes it from the right-hand side. So Leanna, this is right up your alley. You like everything moved to the left. So I get negative 12b plus 5b, which I believe gives me a negative 7b. Bring down the negative 14, bring down the less than or equal to symbol, bring down the positive 14, Now I need to get the variable to the same, excuse me, by itself. What am I going to move next? The negative 14's got to go. So I'll do the opposite and I will add 14 to both sides. That removes the negative 14 from the left, leaving me with a negative 7b is less than or equal to 14 plus 14, which gives me a nice 28. Then what? Divide both sides by the negative 7. So b is now by itself on the left. We said it just a moment ago. Don't forget, when you multiply or divide both sides of an inequality by a negative value, your sign is going to change directions. So my less than or equal to symbol becomes a greater than or equal to symbol. And 28 divided by negative 7 should give me a negative 4.
Now, you said either way, you'll get the same result.
Yeah, so if you had moved the negative 12b there at the beginning, what would have happened is you would have had a positive 7b on the right. The steps would have felt very, very similar all the way through, but at the very end, here we had to flip our sign, but our variable was already on the left. If we had solved it the other way, the variable would have been on the right. We would have had to adjust that, which would have caused the sign to flip anyways. So either way, we would have reached the same result.
We did.
Did you do it the other way?
I did it the other way.
Good. We're growing as individuals. That's fantastic. Now, what we have here, if you recall when we did this in Unit 1, I told you that if you could at least get it to this part here where you had the 2 bits of information and then graph it accurately, I'm going to be thrilled. But technically, usually they're slid back together kind of how they were at the beginning. Now I'll show you how to do that. If you can't do that on the final and you at least get this information and get the right graph, I'm not going to complain. Because in my mind, it makes more sense to look at the answer that way when you're considering the graph. Because if you look at the negative 2, will we have an open or closed circle? According to the sign right here.
No.
The equal to part tells me closed. I want to include it. So I would have a closed circle at negative 2. Make a quick mental note. Which way would we be shading from negative 2? To the left, usually the way it points, as long as you have your variable first. Keep that in your head, because at negative 4, open or closed circle? Closed as well, because it is also equal to. And from there, we would be shading to the right. Well, for and inequalities, we can only accept the region that we would shade for both. And in this case, it's everything in between. Now, for the final solution, again, if you have it split like that still, I'll still give you full credit because in my mind, you still have all the right information. But in most textbooks, normally you're going to see the final solution written back together. The trick I like to use is I always write the smallest number first, which in this case, looking at that number line, is the negative 4. So if I'm looking where the negative 4 was, I need to flip this one around so that it's still pointing at the negative 4. When I put my B, and then I bring in the second half that says that B is also less than or equal to negative 2. And again, I'll say it one more time. If you struggle putting them back together like that, don't panic. I'm going to be more interested in all of your work and your graph. This is just a bonus little exercise that I'd like you to challenge yourself to do, but I will not hold against you if you haven't quite mastered it yet, because it takes a little bit of imagination and it's deceiving. That's why I don't like it. So there is number 7. Number 8. Number 8 is asking for 3 different things: slope, x-intercept, and y-intercept. Now, I would say that the slope and the y-intercept hopefully are the easiest of the 3, because if we could get this equation in slope-intercept form, we would have the slope and the y-intercept, which is why I'm going to start with the hardest one. That's, well, what's usually the hardest one to find for most students, and that is the x-intercept. So for the x-intercept, we go all the way back to unit 2. The x-intercept was the point where our line crossed the x-axis. Well, any point along the x-axis always had a y that was equal to 0. Every y-coordinate for every point on the x-axis was always 0. And it was because of that fact that we could then say, to find the x-intercept, all we had to do was take the equation we were given and replace the y with a 0. So the equation we have, the 4x plus 2y equals 12, would be rewritten as 4x plus 2, and instead of times y, it would be times 0 equals 12. And the reason why we really like zeros in this situation is because anything times 0 is going to be 0, and for our purposes just kind of falls out of the equation. So what we're really left with solving for is 4x equals 12. And how would I solve that?
Divide by the 4.
Divide both sides by the 4. And we get x equals 3. So very quickly, we find the x-intercept of 3. Now, technically, you could use a similar trick for the y-intercept, where instead of replacing the y with 0, you could replace the x with 0. But in my opinion, since you still need to find the slope as well, you might as well get slope-intercept form and just knock out both of those at the same time. So to get it in slope-intercept form, what's a big key of slope-intercept form? How do we know something's in slope-intercept form?
Y.
What about the y? Y equals, or in other words, the y is
Alone.
alone by itself. So I'm going to come over here to this equation. And I want to get the y by itself. What would I move first?
Well, the 4x.
The 4x. So we would subtract the 4x from both sides. That takes it away from the left-hand side, just leaving me with the 2y. Now be careful, look here on the right, 12 and negative 4x, are they like terms?
No.
No, so don't combine things that are not like terms. So I'm just gonna write them side by side. I'm gonna write the negative 4x, and next to it, I'm gonna write the positive 12. What's the last thing we have left to move?
The 2.
The 2, how would we move it?
You would divide it.
And whatever you divide on one side, we're dividing everything by that positive 2. Everything, every single term. So that gets my y by itself. And then on the right, negative 4x divided by 2 is
-2.
negative 2. Don't lose the x. And 12 divided by 2 is 6. Now, just like that, our equation we're given is now in slope-intercept form. And if you think about slope-intercept form, y equals mx plus b, what is my slope? -2. And my y-intercept is +6. Just like that, we find all 3 pieces. All right, moving on to the next page here. Number 9 asks us to sketch the graph of the linear inequality and also answer the following questions. We'll actually answer 9A in the process of graphing it anyways, so that's not too big of a lift there. But the main thing I'm going to highlight here is that this is a linear inequality. So similar to linear equations, we want to go for that slope-intercept form, y by itself. But there is a couple additional bits of information we may need, which I think I'm going to squeeze over here on the right margin. And that is the difference between each of the inequality signs as well as how it affects our final graph. So off to the right here, a less than symbol in our linear inequality is going to give us a dashed line. Shade below. A greater than symbol is going to give us a dashed line, for which we will shade above. Less than or equal to symbol will give us a solid line, for which we'll shade below. And a greater than or equal to sign will give us a solid line, shade above. So again, that's going to be information that will also be provided on a reference sheet for the test. I'm less interested in you memorizing it. I'm more interested in you being able to use that information to graph successfully. Give you another couple seconds there to jot that down, and then we're going to see it in action. So right off the bat, I'm looking at the inequality here, and it may help to imagine the 1, that's the coefficient hiding on the x, because as I'm looking at this, I notice it's not in slope-intercept form, and I really like that y to be by itself. So my works here are going to have to be a little bit more horizontal than I'm used to. But the first thing I notice is I want to move the 1x. So I'm going to subtract 1x from both sides. Which is going to leave me with 2y on the left is less than 2 and negative 1x are not like terms. So I'm just going to write them down. Negative 1x and positive 2. And then I still need to get the y by itself. So I'm going to divide every single term by the 2 that's on the y. Which the y is now by itself. I'm going to have y is less than negative 1x divided by 2. It's not going to divide nicely, but that's okay. I like slopes that are fractions. So here I'm going to have a negative 1/2 x, and then 2 divided by 2 is going to give me a positive 1. So the inequality we started with is now in slope-intercept form. We can start to pick through the information we need to successfully get it on this coordinate plane. So I'm going to jot it down kind of in the order that we're going to need it here. First off, our y-intercept, which is the b in slope-intercept form, is going to be a positive 1. The slope, which is the m in our slope-intercept form, is going to be the negative 1/2. And according to the inequality symbol, which is a less than symbol, that tells me two additional things, and that is that we're going to have a dashed line and that we're going to shade below that line.
What question are we on? 9.
Number 9. So even before I start graphing, if I look at 9A here, I have enough information to answer here. It says, did you use a dashed or solid line? Well, according to the notes I just jotted down, we're going to use a dashed line. Because the inequality sign is not equal to, because without that little equal to bar underneath, we don't actually include the points on the line itself in our set of solutions. Zoom out here just to kind of absorb everything. So we went through the process there, getting the y by itself so that it's in slope intercept form. Identified the pieces of information we needed, the y-intercept, the slope, the type of line, where we're going to shade. Now we're ready to translate all that information or transfer that information to the coordinate plane itself. So my y-intercept that I have listed there is a +1. According to the slope then, a -1/2, I'm going to go down 1, right 2. I'm going to do that a couple more times, down 1, right 2, down 1, right 2. And if I wanted to see a few more points, I could do the exact opposite. I could go up 1, left 2. So I've used my y-intercept, I've used my slope. Now, according to the inequality symbol, we're going to make sure we draw in a dashed line. And then finally, with respect to that line, and remember, you don't have to be super dark in your shading just so it's clear which side of the line you're looking at. We want to include everything that is below our line. And then we move on to 9B, the question that asks, is the point 2, 3 a solution? Why or why not? Now, what I noticed on a past test where we had a similar type question, the biggest mistake that I noticed is I don't think everybody found where that point actually was located. So it may help to actually graph it before you answer the question. So the ordered pair 2, 3 from the origin is 2 units to the right, 3 units up. So this is where that ordered pair 2, 3 is. So the question is whether or not it is a solution. What do you guys think? No, why not?
It's not in the shaded region.
It's not in the shaded region. So we would say no. The point is not a solution because it's not in the shaded region. So only points in the shaded region are considered solutions. And this one point that we were asked to consider is not.
Can you hold it in for a minute?
For just a couple more seconds. If we need to come back later, we can. All right, number 10. Number 10 is asking us to solve a system of equations. So this takes us back, I think this is the first one actually from that unit. This takes us back to unit 3. By far our shortest unit. I think we only had 3 lessons. But we learned a lot of information there and recycled a lot of the same information that we had learned prior. But the big takeaway there was when you're solving systems of equations, you have technically 3 different methods. And they are graphing, substitution, or elimination. Now, technically, all 3 could be used on any system of equations and theoretically would work. Now, I say theoretically because graphing gets a bit tricky. They don't always cross at nice, pretty points that are easy to read. Sometimes they cross way off any size graph that we could possibly have in our possession. So theoretically, yes, graphing would work, but it's not the most practical. We typically rely more heavily on substitution or elimination. Now, looking at the way the system is presented to us, which of those 2 would you suggest we do?
Elimination.
What about it screams elimination?
Because they're already lined up.
They're already lined up. Substitution is much more favorable if you already have one of the variables by themselves. And if you look at these 2 equations, it's going to take a bit of work to get either the x or y from either equation by itself. And actually, it could be done, but in that process, you would temporarily have some fractions that you would have to carry through the process, hoping that they work out. You'd have to be very comfortable with fractions, but it would end up being more of a headache than what it may be worth. So I'm totally in agreement with Tierra. I would personally use elimination as well, based off of her observation that everything's already lined up. But that's only half of what we need. We also need opposite coefficients on either the x's or the y's. Now, right off the bat, we do have the opposite signs, but they have to be exact opposites. Multiplication is our tool here.
I think the bottom one times 2.
Bottom 1 times 2. Talk me through your thought process. What drew you to the bottom equation, and what made you choose to multiply by 2?
Because 7 and 14 can go into each other twice.
So you were focused on the y's, is what I'm hearing.
Yes.
And you're telling me that the 7 can go into the 14 exactly 2 times.
Yes.
Well, boom, that tells me verbally exactly what I need to multiply by. If 7 can go into 14 exactly 2 times, why not go ahead and multiply it by 2? Now, do keep in mind that is going to change the entire equation, which is why I like to wrap mine in parentheses. Do I need to worry about changing the sign as well, or are the signs okay?
The sign's okay.
Signs are okay. They're all right. One's negative, one's positive. I don't want the signs to change. I just want the 7 to become a 14. So as I go through this process, the top equation I leave put. Still have a 5x minus 14y equals a -2. The bottom equation, you want to make sure you multiply that 2 clear through every single term. So 2 times -2x will give me a -4x. 2 times 7y is going to give me that positive 14y I like to see. And 2 times -2 is going to give me a -4. Now, thanks to the process of elimination, when I add these 2 equations together, what actually eliminates?
The 14y.
The 14y with the -14y. Because we changed that very deliberately, we caused the elimination to occur. And then as we add everything else together, 5x plus -4x is going to give me 1x, or just x. We're in luck here. We're not even going to have to solve this one. It's going to solve itself. And -2 plus -4 is going to give me a -6. We're halfway there. What do I still need? I need the y that goes with it, because remember, a system of equations, we're really just asking ourselves, where do these two lines cross? Well, all lines that do cross at a point, and every point is described by an ordered pair. Each ordered pair needs both an x coordinate and the y coordinate. All we have right now is the x. So how do you suggest we find the y?
Plug X in.
Now that we know what x is, we're going to plug it in where? Whichever equation we want. We could use either of the original equations we wanted to, and at this point, it really just comes down to personal preference. If I was doing it, I usually go for the smaller numbers. So me personally, I would choose the bottom equation. But it's up to you. But over to the right here, I'm going to copy down the bottom equation, negative 2x plus 7y equals negative 2. And now that I know that x is negative 6, I'm going to drop it in that equation and get negative 2. And instead of times x, it's going to be times negative 6 plus 7y equals a negative 2. Now, I'm not done with it yet. I've got a little bit of work to do. First off, the parentheses, if we take care of those, negative 2 times negative 6 is going to give me a positive 12 plus 7y equals negative 2. And then I just need to solve for that y, essentially getting it by itself. So let's first subtract the 12 from both sides. Takes it away from the left, leaving me with 7y. Negative 2 take away 12 is negative 14. And then last but not least, I'm going to divide both sides by that 7. Which gives me y equals a negative 2. Now, how do we bring these two parts together?
X and Y. So it would be negative 6 first.
Negative 6 first,
And then
negative 2. Now I got to clarify, are you putting it in that order because that's the order we found them?
no. You always put X first.
In an ordered pair, x always comes first. So regardless of which one you find, x should always be the first value, y should always be the second. Good. So that takes care of number 10. It does look like it's going to rain. It's gotten awfully dark.
It rains.
That's gonna suck. I have to work till closing today. And I'm gonna be stuck in the rain.
All right, number 11, find the product. Product means we are multiplying. And if we recall, if we look at what we're multiplying, we are taking a binomial times a trinomial. Now, if you recall back to unit 4, this was about midway through, no, it was at the beginning of unit 4. When you're multiplying with polynomials, it's really just a big fancy form of distribution, just with more pieces to keep track of. And the way that I like to keep track of it is by using a box. I'll put that down underneath here just as a reminder. And what's great about that box is it can grow to fit pretty much any situation. So a binomial times a trinomial, I'm going to need a 2 by 3 box. So I'm going to do 2 rows, 3 columns. May have went a little bit overboard here on the size, but that's okay. Also didn't separate them evenly. All right, I'm going to try grow as a person and not let that bother me. So the binomial I'm going to use to identify my rows. So I'll use the binomial 2a plus 3. 2a will label my top row. 3 will label my bottom row. And then I'll take the trinomial to label my columns. So the first column is going to be the 5a squared. Second one will be the negative, and I'm going to go and put the negative 1 there visibly so I can remember it. Negative 1a will be my second column. Positive 6 will be my third column. Then all that's left to do is to fill each of these sections by multiplying whichever row I'm in by whichever column I'm in. And I like to just start in the top left corner because it's like reading a book. So starting at the top left, 2a times 5a squared.
10a squared.
Almost.
To the third,
10a to the third. Why does the exponent grow?
because you're adding an extra A.
That's correct. Remember, there's a 1 hiding there on that exponent. And if it helps, there's one down here as well. When you multiply common bases, like these a's, you add their exponents together. That's why they increase. Going to the right, 2a times a negative 1a.
Negative 2a squared.
Negative 2a squared. And then going to the right from there, 2a times 6.
12a to the first.
12a to the first. I'm just going to write 12a, but absolutely same thing. So we did all the multiplications with the 2a. Now I move down to the second row with the 3. 3 times 5a squared.
15A squared,
15a squared. 3 times negative 1a.
negative 3A,
Negative 3a. And 3 times 6
18.
is 18. And here's my favorite part about this box. If you check your diagonals, and in this case, we actually have 2 sets. If you check your diagonals, you're going to notice that you have some like terms that you can add together as you're writing these out in descending order. So the first term I have is the 10a to the third, which is by itself, no like term to combine with it. Then I get the 15a squared and the negative 2a squared, which make
13A squared,
13a squared. I'm glad you didn't touch the exponents. When we're talking like terms, exponents do not change. So we get 13a squared. What about the negative 3a and positive 12a?
9A,
They give us a positive 9a. And then the 18
just 18.
is just 18. Now, if you're a very visual person like I am, if this helps, color code it. The 13a squared is just from combining the like terms that are green. The 9a is from combining the like terms that are in orange. Again, I'm not saying you have to highlight when you do it, just visual cues helps me remember. All right. Number 12. Well, there's that word again. Factor. So I'm just going to put a little mental reminder here. We talked about factoring already back on page 1. So if you're like, I'm not sure what to do in this situation, going back to page 1, we talked about a lot of things when it came to factoring, but hopefully one of them is something we always remember, and that is to always check for what?
Greatest common factor.
Always check for a greatest common factor before doing anything else. Can you think of any greatest common factors here?
No,
No. 16 has factors of what? 1 and 16, 2 and 8, 4 and 4. 25 has factors 1 and 25, 5 and 5. So the only thing they have in common is a 1. That's not going to help me here. But then I go back and I realize if I look at page 1, 2 terms, I think you said it before, Leanna,
perfect square.
they are perfect squares. Specifically, this is a scenario where we are looking at the difference of perfect squares. And in order to factor this, I need to know exactly what is being squared in order to figure out the binomials. What is being squared to make 16x squared?
4X,
A 4 and an x. And what is being squared to make the 25?
5,
A 5. Now, be careful here because there are 2 options that have 4x and 5. Which one is the correct one?
D,
Why not A?
because they're both subtracted, you one addition and one subtraction.
Good. So the difference of perfect squares, it says that once you figure out what's being squared, you use those in both binomials, but one of them has to be positive or addition. One of them has to have subtraction. A doesn't work because they're both subtraction. That would give you a trinomial if you were to multiply those together. Hopefully B and C are throwaways. Hopefully we can clearly see that if you recognize that they're perfect squares and you identify the 4x and the 5, B and C should not make sense at all at that point. But again, that's assuming that you recognize difference of perfect squares, which I'm trying to give you all the clues now so that on test time, you're like, aha, got it. All right. What's that? Our third page we finished? We're getting there. Moving on to number 13, solve the following radical equation. So we talked a lot about simplifying radicals. We did not, however, talk about solving equations that had radicals in them. It's actually a fun lesson. I'm hoping to actually get to it next term because it's 9 weeks long. We didn't get to it this term, so it wouldn't be fair for me to test you on it. So 13 you can throw away. Which is nice because then we go to 14 and we see 14 is going to take some work because we're solving a quadratic equation again, but this time, instead of using factoring, it's specifically asking us to use the quadratic formula. And as a reminder, it says, be sure to round your answer to the nearest hundredth as needed. So, because I have a little extra space up here, I'm going to squeeze in the quadratic formula up here just as a reminder. Again, this of course would be something I would give to you on the reference sheet, but because we're making our review packet as robust as possible, here is the quadratic formula. So it is x equals negative b plus or minus the square root of b squared minus 4 times a times c, that entire thing over 2a. Now remember though, this only works when it's in the following, well, the format here, ax squared plus bx plus c equals 0. Has to be in descending order, has to be set equal to 0, just like when we were factoring. It kind of follows some of the same guidelines there. I guess I should kind of say that this is a side note. So this is the format. And that's how we pull out our A, B, and C to drop in to the quadratic formula. Again, this is one of the more recent topics. This was, I think, the very last one we covered in Unit 4. So hopefully this one's a little bit fresher in your mind. It does take time, but a bit of organization, this doesn't become as difficult. So we have that jotted down, hopefully. Let's take a look at the equation we're dealing with. And what's my concern?
It's not equal to 0.
It is not equal to 0. And in fact, this one's a little bit unique because technically, if I was being lazy, I would move the 9n squared, but then it's still kind of jumbled out of order. So you kind of have some options here. I'm gonna take the lead on this one just a little bit. If I was working this problem, I would actually move the 2 terms off the right-hand side. I'm gonna have to rewrite the order anyways.
I moved the negative n, or the n to the second, and just rewrote it.
You can do that too.
I just fit it in where it goes,
The-
and then wrote it in descending order.
The good news is we've got a couple ways we could go through this. I personally, if I was doing it, I would subtract the 7n over here. And I would also subtract the 4 from over here, put a little guideline in so I can see my little wall. On the right, the 4 minus 4 is gone. 7n minus 7n is gone. on the left, thinking descending order, I should have 9n squared minus 7n minus 4 equals 0. So set equal to 0 in descending order. What is my A?
9,
A is 9. My B
-7,
is -7. And my C
-4.
is a -4. That's going to be my A, B, and C I use in my quadratic formula. So I don't want to lose those. So I come over here to the right, hoping to have a little bit or enough space here. My variable is an n technically this time, so I'll say that n equals negative of b, which I'm going to replace with a -7, plus or minus the square root of b, which is -7 squared, minus 4 times a, which is 9, times c, which is a -4. And then the entire thing is over 2 times a. A, of course, is still 9. And again, because we're reviewing, I'll go this extra little mile here. Anywhere we saw an A, where we dropped our 9s. Anywhere we saw a B is where we dropped our -7s. Anywhere we saw C, where we put a -4. Anything else that I didn't highlight, all of that information should have already been there because it's directly from the quadratic formula. All I'm replacing are the A's, B's, and C's. So it almost looks like we create a bigger mess to begin with, but as we go through and address each of these sets of parentheses one at a time, as we recall, it cleans up very nicely, very quickly. So my next step, knocking out these parentheses here, -7 becomes
A +7.
a +7, plus or minus the square root of a -7 squared. So -7 times -7
+49.
is a +49. Here's where I would grab my calculator. -4 times 9 is -36. But then I need to multiply that by -4,
You get a +140.
+144. And then the entire thing is over 2 times 9, which gives me an 18. There's still a little bit more I can simplify here before I can kind of get into the meat of this problem. Inside that radical, the 49 plus 44, we can combine those because they're already grouped together. So I get 7 plus or minus the square root of, what's that?
18.8.
Oh, you're ahead of me here. 144 plus 49.
193.
Is it 193? I believe you. So 7 plus or minus the square root of 193 over 18. It's at this point then, we need to know the approximate value for the square root of 193 because I don't recall that being on our list of perfect squares yesterday. So what is it approximately? Leanne, I heard you saying 13 point something.
892.
13.892. So we'll do 89. Would be to the nearest hundredth. And again, because we're going extra details here, because it's review, just as a reminder, we found this value with the help of our calculator. So I can rewrite this expression or equation to say n equals 7 plus or minus, oh, not the square root, we just approximated, plus or minus 13.89 all over 18. And now that I've cleaned all that up, I am ready to split at the plus or minus. for that. I've kind of got a little crowded here, so I'm gonna split them over here to the right. Oh, and you know what I did do? I know it sounds like a technicality, but technically we're not dealing with an equal sign anymore. Because as soon as we round, we're dealing with approximations. So n is approximately 7 plus 13.89 over 18, or n is approximately 7 minus 13.89 over 18. So solving one of these at a time, 7 plus 13.89 here on the left, 20.89, and when you divide 20.89 by 18,
1.161.
1.161. So 1.16 if we're sticking to the nearest hundredth. And then moving to the right one here, 7 take away 13.89. Is that negative 6.89? And when you divide that by 18,
Negative 0.38.
negative 0.38. And just like that, we find our two solutions are 1.16 and negative 0.38. So again, a lengthy process, but an effective one. Now, quick side note. For anyone who, if you're at home, if you're printing off the final to write directly on it, or for those of you who will be in the building writing directly on it, if at any point you realize, man, he didn't give me enough space here to work, remember, use as many additional pages for work pages as you need. Don't try to fit your work into a small spot. Use as much space as you need to do the best work you can. All right, number 15. Ooh, this is throwing us way, way back. Solve the following algebraic proportion. Algebraic proportion. It feels like we've learned so much since then that we may have forgotten just what we do with algebraic proportions. And that is the very first thing, use cross multiplication. Cross multiplication. Now, if you recall way back when, back in unit 1, I said, hey, if there's some things, multiple pieces grouped together in a numerator or denominator, wrap them in parentheses. Well, since then, we went through our unit 4. We actually have a name for these things. They're called binomials. So on the left here, we have a binomial in the numerator and a binomial in the denominator. We want to make sure that those move as binomials. And that is why we wrap them in parentheses. We just, when we first learned proportions, didn't have that vocabulary yet. But what I'm going to get is I'm going to take the binomial p plus 10, which is the first numerator, and multiply it with the second denominator. So we're looking at 9 times p plus 10. And that's going to equal what we get from cross multiplying the opposite direction. So that's going to pair the 8 with the binomial p minus 7. After that cross multiplication, however, this just becomes a linear equation. We're going to solve it just like we did the problem on the first page. I'm going to go through our steps. First thing that should catch our eye, parentheses. We have 2 sets, so 2 distributions taking place here. So on the left, distributing the 9, I should get 9p plus 90. equals distributing the 8 on the right, 8p minus 56. Second thing I check for are like terms. Do I have any? I do not, because they're not on the same side. So then I go to the third thing. Do I have a variable on both sides?
Yes.
Yeah.
Yes. Which one would you suggest we move? The 8p. And how would you suggest we do it? So we'll subtract 8p from both sides. So it removes it from the right-hand side. On the left, 9p take away 8p is just p plus 90 equals the negative 56 left over on the right-hand side.
You add an E to 90.
Ooh, well, I can't actually add p with 90.
You're subtracting P or 90 and moving it to the 56.
But I do want to get the 90 away, so I subtract the 90 to make it disappear from the side with p, which leaves the p by itself. And then negative 56 take away 90, I believe, is negative 146,
Yeah.
which at this point, students are like, oh, that's way too big of a number. No, it's not. P equals negative 146. Doing really well for time. Number 16. I'm going to end on one that you're going to curse me a little bit, because technically we have all the skills. I just never asked you to exercise them in this particular fashion.
I did yesterday so many times.
Now, I will draw your attention to the fact that it does say select all that apply, which leads me to suspect that there may be more than one that is a correct answer. So I do want to consider all of them before I call it quits. But what it's asking for is for us to solve for the identified variable. Well, we've done solve. We know what solve means. All that's basically telling us to do is to get the variable by itself. You're solving for a variable. Your ultimate goal is to get the variable by itself. Now, what usually rubs people the wrong way on this problem is because you'll notice, unlike all the other equations, there are no values. They're all variables. What you have to remember, before you hate me too quickly, is that variables just represent values that we don't yet know. So when we move them in the same way that we'd be moving values if values were in their place. So we have an equation here. U equals A times K, all divided by B, and we're trying to get which variable by itself? K. We want K by itself. So let's just focus on that. Which side is K currently on?
The right.
It's on the right. So the right side has got my focus first. K is currently being multiplied with A, but all of that is being divided by B. Can you guess what we would do first?
You would remove the B, so multiply the B by both sides.
We want the B gone. Right now, all that's being divided by B. I can't touch AK until B's gone. And I liked what you said. We're going to multiply both sides by B because B is currently being divided. So a quick multiplication will make that disappear. But you got to make sure you do the same thing on both sides. So on the left, we now have B times U, which I'm going to write as BU. On the right, the B and the dividing B eliminate each other, leaving me with just A times K. What are we solving for?
Okay, so
K. Is it by itself? What did you say to do?
divide the A.
Divide both sides by A. So on the right, A divided by A simplifies, it's gone. On the left, it looks a little bit strange. I can't actually divide it into something new, but I can write down what I currently have. I have b times u divided by a equals k. Now,
B and B.
B and D. So Leanna's already looked ahead. She's got this. Now, technically, we try to write the variable first, but use that when you're thinking about your answers. K is by itself. And on the other side, we have B times U, and it's all being divided by A. Leanna's telling me that B and D are the only ones that work. So real quick, let me ask, why does A not work?
Because they're still multiplied, you have to divide the A.
We had to divide the A. I don't see any division. Do you?
No,
Why does C not work?
because it has A B over U when you want UB over A.
Right, we divided by A, we did not divide by U. So it looks like the A and B were swapped around for no good reason. So yes, it is strange because they're all variables, but we use the exact same steps as if we were solving any other equation. Good. So, real quick, for the sake of the video as well, and for you guys, this is where we're going to stop for today. I know we still technically have about another 20 minutes. We probably could squeeze some more problems in. But this is kind of a good halfway mark. And this will be considered part 1 of our final review. So as I said at the start of class, the final review will be broken down into 2 separate videos. Part 1 will be the first half. Part 2, which we'll do on Monday, will be the second half. That way you're not trying to dig through one long video to find what you're looking for. You can kind of orient yourself a little bit easier. So the second half will be coming on Monday.